All right, hello. This is deep neural networks for low-cost eye tracking. So this is uh, in the KES 2020 conference, and it's our machine learning contribution for low-cost eye tracking. Now, I have to confess, although I've been doing eye tracking, my name is Andrew Duhovsky. I'm at School of Computing at Clemson University. Although I've been doing eye tracking for over 20 years, I've never really built an eye tracker. I've always used them, so I've always been a consumer of eye trackers. But here, Ildar Rakhmatulin from South Ural State University in Chelyabinsk, Russia, got in touch with me online, and we talked about this project, and it's mainly all his work here, and so all the credit goes to him for doing this. And so he's got a very nice implementation of a machine learning based, essentially low cost eye tracker that uses a webcam on a pan tilt unit. So let me tell you what that's all about. It's fairly popular right now. The idea is it's in demand. People want to do cheap webcam eye tracking, essentially. And also using open source tools, for example, OpenCV and YOLO, which is exactly what Ildar did here. He also added in a pan tilt unit, which I'll explain in a minute. But the idea is to use open source stuff and try to get cheap eye tracking. I've seen cheap eye tracking in mobile kinds of scenarios. I know that, for example, I had a colleague in Poland who built his own wearable eye tracker for about 35 euros, he said at the time. Rafał Mantiuk, I believe was his name. If you want to look that up, I think we had a tutorial on that at Eurographics at some point. There was a tutorial or a short course, 2013 maybe. But this is a slightly different animal. It is a table-mounted version, so it sits under the computer monitor and not on your head. And so in some ways, these are a little bit more difficult to build because they're farther away. A wearable eye tracker is right next to your eyeball, and so you get a very nice, crisp image of the eye. I actually, well, a student of mine did build one of these one year, and he did build one with these huge cameras that we had, and he was trying to do everything in the visible spectrum. And eventually, I suggested to him that he use infrared light and an infrared bandpass filter for the camera to get rid of reflections off the eyeball, and that worked great. Here, Ildar uses IR for a slightly different purpose. So let's get into it. What we want is low cost, high accuracy, convenient, and flexible. So everybody wants this kind of thing. Eventually, what we would like to see is, of course, eye trackers working in laptop lids like I have over here. So if a laptop lid could do that, maybe we need an IR LED somewhere, and I think they actually are available. I saw a laptop that had a IR LED for face detection, so I don't see it as impossible. Here, Ildar has a pan tilt unit, which is kind of interesting. So why would you want this? Well, Ildar found a bunch of different applications, and actually applications are growing for eye tracking in the wild, whether it's webcam based or wearable in the wild, whatever. And so we're looking at detection of psychological disorders. I know I've done some work with colleagues using a wearable eye tracker to examine differences between psychopaths and non-psychopaths. There's been work done on detection of alcoholism, cognitive assessment, whether maybe you're a slow, fast learner, dyslexia, that sort of thing, speech in children with dyslexia. There's a fascinating region for understanding programming, not only C, but programmers in general, pair programming, for example. There was actually a small conference called EMIP, E-M-I-P, eye movements in programming that look specifically at that. Mental fatigue, for example, and vigilance when you're looking at a driver of a car or a pilot in an aircraft, that sort of thing. So there's applications are actually growing all the time. And so there is quite a need for cheap and easy to use eye tracking solutions. So what's been done in the past using these kinds of approaches? And so the IR light for corneal reflection is usually a fairly popular one. What happens is the computer vision task is to look for the corneal reflection of the IR. That gives you a reference point, which essentially does away with head rotations. Once you have that, and you have a person that looks at 5 points, usually like a calibration sequence here, 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 here. Well, I've got the background on from the Zoom talk. So anyway, 5 points on the screen. Then you've got your IR reflection and pupil center as the vector, which you can then interpolate anywhere on the screen. And that's been around for the last 20 or more years, and it's very popular. For webcam and any kind of high-res imaging, superpixel segmentation is coming into play, and the task is pretty much the same. Find the pupil diameter, distinguish it, find the pupil center. You'll get the pupil diameter as well, which is also interesting for pupillometry sake. But find the pupil center, find out what the eye is looking at, and then do something about head rotation and head translation. So those are the problems that are there. So that's why you see inertial measurement, for example, to like an inertial kind of tracker for head position and head movements. Neural networks are coming into vogue to obtain head posture estimation, which is pretty interesting, head pose estimation. And of course, the Viola-Jones classifier has been used for a long time for finding the face in the image, which is usually where one starts when developing this kind of a thing. So in Ildar's solution here, he uses the Viola-Jones classifier to obtaining, well, not necessarily head pose estimation, rather just finding the box where the face is. I think you have to do a little bit more work to get the head pose out of that. YOLO V3 for the eye position, so that's essentially, given a head box, we want to find where the eyes are inside, and then in some way zoom in to find out which way the eye is pointing. The LED he uses for head movements instead of inertia. He uses color coding for labeling of the regions. And he says that webcam, since it's a low-res camera typically, won't allow superpixel segmentation, but he uses the IR light to compensate for head movements in concert with the pan tilt unit that you'll see in a bit. So from our background, it seems like our approach is fairly similar to Krafka et al.'s gaze capture software, where this is called the Eye Tracking for Everyone paper, which was kind of interesting. It came out of MIT a few years ago, and they actually wrote an app that you could download and put on your smartphone or smart pad or whatever, and then you would play this, and then they would, with your permission, capture images of the eyes. So they captured almost 2.5 million pictures, and then they would train the convolutional neural network to find the eyes. And so we use similar kinds of techniques, but maybe in a slightly different sequence, which is here. So first we find the face, which is the Viola-Jones traditional kind of detection. Facial features, find the eye. Where's the eye? Then use the neural network to figure out the gaze detection, so train that. And then use the infrared light to compensate for head movements. And then finally, you'll see there's dual coordinate systems to feed the eye coordinates into the computer coordinates. Okay, so here's the image pre-processing, and it's all open source. You can do a good deal of this yourself. Find the face contour with OpenCV, so this is the Viola-Jones detector. Hard cascading filters work nicely here to find the face. In fact, they come with specific detectors for the eye regions, nose and mouth, which work pretty well. On top of that, you can also used the dlib library to find what are essentially the facial action coding system points. And here we use 68, I believe the number is. And from that, you can find the eye center, and then even get a little bit more and get the eye regions if you just connect the points, essentially. Yeah, so 68 face landmarks is what we use from dlib. You can actually do some nice expression analysis here, which is kind of cool, but slightly different topic. But what he uses this for, what Ildar uses this for, is he uses specific points, the 36 to 41 points, to figure out where the eyes are. And then what he does, which is rather kind of interesting, is he then actually grows this region out to give it a slightly larger search area for the pupil center to find out which way the eye is oriented. So he expands these by 20 millimeters to get a region of interest, or ROI, in the OpenCV code. Okay, after that, Ildar explored several neural networks, YOLO v3, SSD. YOLO is YOLO, you only look once, SSD, MaskR, CNN, and FreezeNet. And also the data sets that can be used for non-commercial training purposes. And from these, though, he found eventually, he says in the paper, that you couldn't quite use these. Some of them are maybe only for medical applications or things like that. So here he used a custom data set of 3,000 images from 3 people, and he chose the YOLO v3 machine learning approach. So here's the images, a subset of that he used for gaze detection. This is the YOLO training. This is after the dlib point growing and ROI segmentation in OpenCV. He used the annotation tool master program, which is open source, to label the eye looking left, eye looking in the middle, eye looking at right, and the palpebral fissure corners. So he labeled these by hand, I believe, or using this tool to train train YOLO. And so YOLO, once trained, will yield gaze position relative to point 1 that is identified here as the inner palpebral fissure. And the other features you can get are the iris and pupil. So he's got those color labeled as 2 and 3 there after training. So the point here is, though, you get the X and Y coordinates with respect to number 1 there, the inner fissure. Right, and once you have that, you also need to look at the second coordinate system, which is essentially not the eye coordinate system, but not the eye image coordinate system, but the camera relative coordinate system, which he's got the point for calibration is the IR light at the bottom of the screen. And then the camera tracks the head with respect to that, so you can map one coordinate system, transform it to the other. All right, camera focus is controlled by a simple neural network, another one, and he's got 4 stages for classification. I'll refer you to the paper for further details, but he uses that to orient the camera using the pan, tilt, and autofocus features. And he's got a servo motor there controlled by a Raspberry Pi 3, which he says was fairly straightforward to put together. So, empirical results, resolution 1000 by 1200 at about a cost of $25, which is pretty good. So it's actually maybe a few dollars cheaper than Rafael Montiuk's 35 euro eye tracker, but that was wearable or head mounted. Okay, and what you also need to show for eye tracking kind of work is the average error. And so here he recorded on a 5x4 grid of points. You can see the individual errors, and if you average those up, you get about 2.2 degrees average error. Now you can see that in some cases it was as bad as 3.3 degrees, but in other places it was as good as less than 1 degree error. And typically you compute that, because if you know the point here, let's see if we can have a point here and a bunch of points that you collect or sample here, well, you can figure out the distance and then obtain the average to get the average error. Sampling rate is camera dependent, which is 30 hertz. All right, and that'll do it, I think, for me. Thank you very much. I'll be happy to try to answer some questions, but keep in mind that this work is pretty much all due to Ildar and not myself, so I can try to answer as best I can. But if I can't, I will refer you to our paper for further details. Thank you so much.